The process going on here isn't too complicated. We have molybdenum chunks holding a lot of energy. They're hot. Hot metal goes in cold water. Energy is transferred from the hot metal to the cold water until both the water and metal reach thermal equilibrium, which just means they reach the same temperature. So the main concept here is assuming there's no heat lost to the surroundings. The conservation of energy tells us that the heat gained by the water plus the heat gained by the molybdenum, which is, it's not gained, it's lost, so this would be a negative here. So the total change in heat of the water plus the total change in heat of the molybdenum is 0. To write that in a way that makes more sense, we can say that the heat gained by the water equals the heat lost by the molybdenum. Now we just realized that we know equations for heat, Q. Q equals mc delta T, and we are on our way. When writing mc delta T for the Q water, we have to be very sure that we make it clear that this is the mass of the water, the specific heat of liquid water, and the change in temperature of the water. And we do the same thing for the Q of molybdenum. And now we have done something important. We have introduced the variable that we want to solve for, the specific heat capacity of molybdenum. So let's solve for that variable by isolating it, dividing both sides of this equation by the mass of molybdenum and the change in temperature of molybdenum, so that they both cancel on the right side. And we are left with a whole mess of variables. But we can be confident that we can figure out what they are, or we know what they are because they're given. So let's figure them out. Aha! Wait. But first, you might have been bothered by the disappearance of this negative sign. And that should have bothered you, because I forgot to keep it. So, to be technically correct, we need that minus sign to stick around. Now we can figure out the identities of these variables. The masses of water and molybdenum are given in the question. We have seen the specific heat capacity of water before. The change in temperature of water is the final temperature of the water minus the initial temperature of the water, which is positive 5.3 degrees because it increased. The temperature change of the molybdenum is the final temperature of the molybdenum minus the initial temperature of the molybdenum. In this case, the temperature decreases, so the final temperature is lower than the initial temperature. So we're going to get a negative number as our temperature change for molybdenum. We have done a pretty good job of figuring out the numeric value of all these tangled mess of variables. So let's put those numbers in. Now that we have our numbers in place of the variables, the first thing I want to do is cancel these negative signs because those are obnoxious. So now we can just work with all positive numbers. And we know that the specific heat capacity has to be positive. It wouldn't make any sense to be negative. My calculator tells me the answer is this.
Made with Doodlecast Pro.